I'll be finishing up the examples for 7.2 in your notes, and I'll just check the notes in class. It'll count as a homework assignment. So make sure you write them neatly. I'm going to be doing part B here next. It's the same region throughout all of this example, so although it got clipped off, I'll redraw it for you. Was the region formed by intersecting the line y equals x with the curve y equals x squared, and that was the region that was bound by both. And we shade that region in. And then we go look at what we're revolving it around. In this case, we're revolving it around the line y is equal to -5. So I'm going to go way down here. And I'm going to have my axis of rotation. I'm going to put that in red. So like that. And I'm rotating about y equals 5. I draw my rectangle perpendicular to the axis of rotation. It's going to be empty until I hit the outer edge of this curve, or inner edge, and then I will have a solid piece. So kind of consider it on an invisible thread, or like a piece of dental floss, and you're going to be whipping that around. You're going to have a gigantic hole created in the center. If you can picture what that's going to look like, you don't necessarily have to draw it, but down here is where you'd have that curve replicated, and then it have like a circular bottom, and you can kind of picture, that's not the best picture, but what that's going to look like. It's going to have a huge hole in the middle of it. So next step, we need to decide what kind of a problem we have here. We have a dx problem, and it's a washer problem because of the hole in the middle. And I'd get all this organized. This requires the capital R, and we could call that R of x if you want, but just so you know, because it's a dx problem, it's going to have x's in it. Sometimes that's helpful. This is given as the axis, the distance from the axis to the outer edge of the curve, and it's a distance. So I'm going to write axis to outer edge. It's this right here. And whenever we find the distance between two things, we do top minus bottom. In this case, the top, or the outer edge of that curve, is the line y equals x. So it's going to be x, and then we do minus, and then we do the bottom. So it's top minus bottom. So it's going to be x minus -5 or x plus 5. And you can kind of see how that makes sense because I wish I had another color here. Well, from here to here is x, and then from here to here is 5, so the whole distance is x plus 5. You can visually see that, but I do think the top minus bottom is helpful when they get a little more confusing. The inner radius is going to be, again, this inside hole right here, and again, that's the axis to the inner edge of the curve, axis to inner edge. And again, that means we do the top minus the bottom. The top of that region is the inner edge of the curve, which is x squared. The bottom is -5, so I'd have minus -5, and that would become x squared plus 5, which again makes sense because x squared is this distance here, and then there's 5 more to go that way. But just think top minus bottom, and one of them is always the axis of rotation, which over here was a 0, but I've taken my axis of rotation on this one and moved it down 5. So now I need to set up my integral. I'm going to integrate along the x-axis. I need to remember my pi, and I'm going to be going from 0 to the intersection, which is at 1. So I'm going to integrate from 0 to 1, capital R squared, which is right here, my x plus 5 quantity squared, minus baby r squared, which is x squared plus 5 quantity squared with respect to x. And then I just take note of whether I'm doing a calculator active problem or a problem that I have to do by hand. Again, if I have to do it by hand, it requires me to FOIL in that integrand. So I'm going to have x plus 5 times x plus 5. And then I'm going to remember minus, and I'd put beefy brackets so you don't make a sign error. And I would have x to the 4th when I FOIL that. Then I'll have plus 10x squared and plus 25. The whole problem is with a differential along the x-axis. And then you'd clean up your algebra. You do your antiderivative from 0 to 1. So we'd still have the pi. We would have x squared, and I might as well write it all out, x squared plus 10x plus 25, and then minus x to the fourth, and then this is where mistakes start to happen. So again, those beefy brackets are always a good idea. Then clean up your integrand, and I'm going to write it in descending order of the exponent. So I've got a negative x to the fourth. I've got x squared minus 10x squared for minus 9x squared. I've got a 10x and no more x's. And I had a plus 25 minus 25. Boom. And I still haven't integrated yet. So now I do the antiderivatives, and then I'm going to quit. Negative x to the fifth over 5 minus 9x cubed over 3, which I'd simplify, plus 10x squared over 2, which I'd also simplify, and then I go from 0 to 1. I'll leave the arithmetic on that one undone. So the next one is part C. I need to go see what I am going to be revolving around for part C. Oh, come on. Part C, we're revolving around the line y equals 2. So we're going to have this exact same region. And again, we're just going to be changing that axis of rotation. So let's go down here, part C. I can't grab a hold of it here. Oh, there it is. All right, so we'll put part C right here. And I'll draw that exact same picture. Again, it's the same region. We're just changing our axis of rotation, and it changes the problem significantly. So it's y equals x squared, intersecting at 1, 1, obviously. Shading it in. Axis of rotation now is the line y equals 2. So I got to move up the y-axis here a little bit. This is 1. So I'm going to go right up here at y equals 2 and draw an axis of rotation. It's always helpful if you have multiple colors to kind of maybe put your axis of rotation always in the same color. I'm going to put mine in red right here, or make it extra thick or something, but I'm going to be revolving that way. So again, the process will not change, and you should get very systematic about how you approach these. A good sketch, shade it in, axis of rotation, bold. Draw your representative rectangle from the axis. It's going to be empty, 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 to the curve. So that's my representative rectangle drawn perpendicular to the axis of rotation. You're going to picture whipping that sucker around this line, and remember that's the line y equals 2. So again, I'm going to call this a dx problem and understand that I am going to have washers created because of that hole in the middle. I need to find my capital R, which will be with respect to x. Capital R is the distance from the axis to the outer edge of the curve, and then I just do top minus bottom. The top function is 2. The bottom function is the curve x squared. So again, that capital R, just think axis to outer edge, and then it's top of those two minus bottom of those two. And then that gives you a very definitive way of calculating your radii. Your inner radius, again, is the distance from the axis of rotation right here to the inner edge of your curve. It's that piece of dental floss in there. And again, we just do top minus bottom. And that'll give you a very good way of getting those radii. Then I'm going to set up my integral. It's pi times the integral from, again, I'm still going along the x-axis, from 0 to 1 of big R squared minus little r squared with respect to x. And then this again, you would FOIL, beefy brackets when you do, and then watch your arithmetic. Or if it's calculator active, you would math 9. And I will leave that one undone. All right, so next up, part D. Got to, again, go see my axis of rotation for this one. So I'm going to move on up so I can see the problem. My smartboard's having to think too much. All right, so for part, what one am I on? Uh-oh. I think I did, for part D, I did it in the B slot. Oh, I did. All right, well, let's do this. I never did B. This is D. And now I'll go do E. That'll be easier than trying to fix it. So let's go do E. It's about x equals -1. So this is the only one where I'm actually having a vertical axis of rotation. It's the line x equals -1. So, and again, part D, I already did up above there, so you can just go point. Part E, I am about the line x equals -1. So again, same region. Let's go draw it. If you don't have much room, just draw it on the back of your note packet or something. It's x equals y, or y equals x, and it's the parabola y equals x squared, intersecting at 1, 1. Shade it in. Draw your axis of rotation, x equals -1. I'm going to do it in red. I think that's a good idea. Always do your axes in the same different color from your work so you don't lose track of what you're rotating around. I draw my representative rectangle from the axis perpendicular. Dental floss, then solid. I realize that I have a dy problem and I'm going this way. So this would be called a washer problem with respect to y. So now I know I'm going to be climbing up the y-axis. My integrand is going to have my outer radius, and my inner radius in terms of y. So sometimes it helps to label them as like functions of y. So again, my outer radius is the distance from the axis to the outer edge, which now is going to become right minus left, but it's again going to have to be solved for y. So that outer curve is y equals x squared, which means that x is the square root of y. Technically plus or minus, but this one is up above the curve. So I'm going to have y root y. And if that confuses you, kind of think about if this curve kept going, it would have the point 2 comma 2 squared on it. Well, it also has the 4 comma square root 4 on it if you were to talk about it in terms of y being the independent variable. All right. So my big radius is the distance from the axis of rotation to the outer edge of the curve. It's going to be right minus left. And the left one on this case is a -1. So it's going to be root y plus 1. Similarly, my inside radius is the distance from the axis of rotation. Basically, it's the dental floss to the inner edge of the curve. And again, I'm going to do right minus left. And this is the line y equals x, so you can think of it as xx or yy. But it's going to be y minus right minus left. And that's the trickiest part, is getting those radii down. So I don't want to under stress it. It's always axis to outer edge, axis to inner edge, but then to decide which one comes first, it's right minus left. Or if it was a dx problem, it's top minus bottom. So then when I set up my integral for this, I'm going to be integrating up the y-axis, but that'll be the same for this one because that was the point 1, 1, so they were the same. I don't forget my pi out front. I do big R squared, root y plus 1, quantity squared, minus y plus 1 quantity squared. It's r squared minus r squared, dy. And then again, I'd FOIL this. So I'm going to get a pi times root y is just y. And then I'm going to get outer root y plus inner root y, which will be 2 root y, plus 1, minus beefy brackets, FOIL the next one, y squared plus 2y plus 1. And then the rest would be integration and arithmetic. And with the limits, so I'm not going to complete that part either. So one more example, and that'll be it for the notes. It's a long set of notes, but they're important. So with this one, example number 7, let's see if I can move it in here. It says, find the volume of the solid formed by revolving this parabola. So let's go get a good sketch. I'm even going to give myself a little more room on that one. Sorry about that. A nice good sketch, don't make them too tiny. It's x squared plus 1. So let's have that be 1. It's going to be a parabola, and I'll decide what part of this I need after I draw it. And the line y equals 0, aka the x-axis. The line x equals 0, aka the y-axis, and x equals 1. Okay, this one's going to be a little trickier. So we're going to shade this in. I'm going to take the time to shade it. And watch when I'm shading. Do you see this rectangular part down on the bottom? From 0 up to 1, because that's what this is, I have a disk because there's no gap between my rectangle and my axis of rotation because I'm going about the y-axis on this one. But I'm going to use a different color on here for this part. I'm going to have washers. So this problem is going to have a solid base. If you were to picture this whipping around the y-axis, it's going to have a solid base on the bottom, and then it's going to have a one with a hole in it on the top. So when you draw your representative rectangle, it shifts here because right here it butts up against the axis, and I have a disk. But if I were to, I'm integrating up the y-axis, once I get up to this part, then I've got a hole in it. So I have to make two different problems. Both of them will be dy because I'm going around a vertical axis of rotation. So this is going to be a dy problem, but it's going to be disks for a little bit plus washers for the rest of it. All right, so we've got to figure that out. In order to do that, for my disk, I need my radius. Well, it's consistent all the way along here. No matter where I drew that rectangle in this part, it's 1. So my big radius, and I guess you could write of y, equals 1. But for the washer, I need the little radius as well. The big radius will continue to be 1 all the way around there, but my little radius, again, is this little piece of dental floss from the axis to the inner edge of the curve. And we do right, which in this case is the curve, squared plus 1, minus left, which is just 0 because it's the y-axis. But again, it's important that you think of right minus left because if I'd moved the axis of rotation over here to -1, it would have been x squared plus 1 minus -1, or equivalently adding this distance of 1 onto the inner radius. So that's really important. But on this one, it's just x squared plus 1. However, I've got an issue here. Because remember, that can't happen. That's why it helps to write that. So although you'd be tempted to put in an x squared plus 1 there, that's if you were to write it as x comma x squared plus 1. But that isn't the right part of the function. So what I need to do is I need to solve that for x. I'd say y minus 1 is equal to x squared plus or minus square root y minus 1 is equal to x. And I'm on the positive because I'm up above there. So I've got root y minus 1. If I were to point at that point, instead of labeling it x comma x squared plus 1, I'm going to have my independent variable be the y, and that'll determine the x as root y minus 1. So you've got to be very careful with that and watch your variables. They must match. My limits need to be in terms of y for this problem because it's a dy problem. My radii need to be in terms of y, and I need to have a dy on the end of my integrand. So my inner radius is actually the square root of y minus 1, minus 0 technically. So let's go set up our integral. So we've got disks. I'm going to scroll a little bit here. So we're going to split that into the two pieces. That green part will be from 0 to 1. I have a disk, and the radius is consistently 1. Then, for the red part, from 1 on up to 2, I have washers. That requires, I forgot my pi, that requires big R, 1 squared, minus little r, y minus 1 quantity squared with respect to y. Now, for those of you who understand it, this shouldn't surprise you what happens here. The antiderivative of 1 with respect to y is just y, so I get pi times y evaluated from 0 to 1, or basically just 1 pi minus 0, or pi. That's what that bottom green part is contributing to the volume. Well, let's remember some geometry. For geometry, that bottom green part would have been contributing this to the bottom of the entire solid. And this is just a cylinder. It had a radius of 1 right here. It had a height of 1. And from geometry, if we did pi r squared h, we can see that that green is just contributing pi to the volume of the whole thing, just because that radius isn't changing, so we didn't really need to have a differential for it, but it works either way. This one, though, we need calculus for the red part. So once I continue on here, I've got pi plus, and in red, pi times the integral from 1 to 2 of 1 minus beefy brackets, y minus 1 quantity squared is just y minus 1 with respect to y. So I'm going to just let this pi hang along and try not to forget about it at the end. This would be pi times the integral from 1 to 2 of 2 minus y dy. So the red part is going to contribute pi times 2y minus y squared over 2 when I do the antiderivative from 1 up to 2. And plug in a 2 in here. I'd get pi times the integral of 4 minus 1/2 minus more beefy brackets, putting in the 1, 2 minus, oh, I have a mistake there. When I plug in a 2 here, it'd be 4 minus 2 squared over 2 is just 2. I'm getting sloppy here at the end. And then I get minus, putting this one in 2, minus 1/2. I'd have to remember I had the pi in front of it. I also had the pi contributing from the bottom, and then I'll leave it to you to finish the arithmetic for that one. But it's pretty doable. Looks like I'm going to get 3 halves out of that one, right? Because I'm going to have 2 minus 1/2. So that's going to give me pi right here from the green still, plus pi times 1/2, or pi plus pi halves, or 3 pi halves. And that's it. Have a good one.